Hello, this is Gregory Maxwell, and in this lesson, we will be talking about integer exponents, their properties, rules of exponents interpretation, and their operations. Integer exponents, properties, rules, and operations. The PowerPoint presentation here, some of the slides were taken from work done by Professor Shauna Hader at Salt Lake Community College. So I just want to give her the credit for her slides. Let's move into the topic now. So first of all, what are exponents? Exponents basically have are a part of a number which is called a power. A power of a number is a number raised to a certain exponent. For example, in this case, 2 to the 5 is a power of 2, and 2 to the 5 works out to be 32, as we'll see in a minute. So 32 is a power of 2. The exponent is a number at the top here. So the 2 is called the base, and the 5 is called the exponent. And the exponent tells us how many times we multiply the base by itself. Well, that I should say the positive integer exponent tells us how many times the base is multiplied by itself. So this 2 to the 5 means 2 multiplied by itself 5 times. So we have 5 factors here, 2 times 2 times 2 times 2 times 2, and that is 32. So again, that is an exponent. Number raised to an exponent is the power. The base is the number that's raised to the exponent. The exponent is written at the top right hand corner, and that tells us if it's a positive integer, it tells us how many times the number is multiplied by itself. 2 to the 5 is 2 multiplied by itself 5 times, and that gives 32. Now let's talk a little bit about laws of exponents. So let's see here. The first law of exponent, apart from the definition itself, is what happens when you multiply two numbers with the same base, and then what happens with that? Well, you add the exponents, and I'm about to explain that in a minute, but I want to show that there's a comparative law for division. And the law for division is if you divide two numbers with the same base, then you subtract the exponent. And thirdly, if you raise a number that already is raised to a power, so you have a power, and that means that the base raised to an exponent, and you raise that expression to another exponent, really what you should do is multiply the exponents. So let's see what that means in examples. Now, I'm not going to prove these rules for you because these proofs require a method called mathematical induction, but they're not hard to understand. So what I'm going to do is I'm going to explain this rule with an example. I'm going to illustrate the rule with an example. So let's say I multiply x to the 7 multiplied by, say, x to the power 4. X to the 7 multiplied by x to the 4. Really what we're saying here with this x to the 7 is that we have 7 x's multiplied together. X times x times x times x times x times x times x. So we have 7 x's multiplied together here. That's those 7 right there. Let me write that in red. Then we're going to multiply that to 4 more x's multiplied together. X times x times x times x. So as you can see, I'm multiplying 7 x's that are multiplied together, a product of 7 x's by a product of another 4 x's. That's what I mean by x to the 7 multiplied by x to the 4. And of course, that means that when I put them all together, I'm really adding the 11 x's plus the 4 x's, and that gives me, sorry, the 7 x's plus the 4 x's, and that gives me 11 of them in all. So that what we ended up doing is we ended up adding the exponents, because really we're counting how many x's do we multiply in all. We take the 7 from the first product, the first exponent, first power, and then the 4 from the other power and add those together. This is why we needed the bases to be the same, because we couldn't have added the exponents, otherwise we'd be counting different things. So there we have 7 plus 4 is equal to 11. If we're doing the division, let's do that. We can write it two ways. We could write it as x to the 7 divided by x to the 4, or we could write that as a fraction, x to the 7 over x to the 4. If you look at that, really what we're saying is that we have 7x's multiplied in the numerator, x times x times x times x times x times x times another x, that's 7x's, divided by 4x's at the bottom, x times x times x times x. As you can see, since we're dividing here, we're dividing a product by a product, we can use that fact that division is an inverse operation, and we can then say, oh, we can just cancel this x with that x. That's 2x, one x cancel with one at the bottom, another x cancel with another x cancel with another, and another x cancel with another. So what we've ended up doing is we have taken out 4 of the x's from the numerator, leaving 3 of them behind. And we've canceled all the x's in the denominator, so we end up with x. So effectively what we've done is subtracted the exponent of the denominator from the exponent of the numerator, leaving 3 x's behind. And that's the idea behind dividing by the same base. We couldn't have canceled if the bases were not the same, so it is important that the bases are the same. Now we're going to do another example here. Let me just separate these two examples with a nice line here so that we don't get them confused in our explanations. And then the third example I'm going to do here is what happens when we raise them to a power. And some of you may be able to start seeing what's going to happen. Really, we're saying, for example, x to the 7 raised to the power 4. What that really means is that I'm multiplying this term by itself 4 times, x to the 7 times x to the 7 times x to the 7 times x to the 7, which means I'm going to, all the bases are the same, so I'm just going to add the exponent to themselves. 7 plus 7 plus 7 plus 7. But when you add a number to itself repeatedly, that is the same as multiplying it by itself that number of times. Multiplying it by that number of times, I mean, not by itself, but multiplying that number of times. So when I add 7 to itself 4 times, I'm actually multiplying 7 by 4, gives you the same result. So the answer, therefore, is going to be, and let me write it as x to the 7 times 4 is 28, x to the 28, which means I have 28 x's multiplied together there. And those are 3 of the basic laws of exponents. Now, those laws give rise to another situation. What if you multiply 2 things together and then raise that product to an exponent? Or what if you divide 2 things and raise that division, that quotient, to an exponent? Well, the rule is that the exponent gets distributed over the product or over the quotient, but it has to be all multiplied or all divided or some combination of those two. It cannot be mixed with addition or subtraction. So the exponent gets multiplied to each term in the product or each term in the quotient, each factor in the product or each part in the quotient. And I'm going to illustrate that with an example here. Let's say I'm going to use 2 different variables here, v multiplied by w. And let's say we raise those to the power 4. Well, what that means is we're multiplying v times w 4 times. And that means, since multiplication of real numbers is commutative and associative, I don't need the parentheses because of the associative property. And I can rearrange these so I can put all the v's together, and I can put all the w's together. That's the commutative property of real numbers. And what you recognize is that we end up with 4 v's multiplied together and 4 w's multiplied together. And there you have it. When I raise the product to an exponent of 4, each part of the product, each factor in the product gets raised to that power. The same thing happens when we raise a quotient to an exponent. So let's say I have m over n raised to the power 7. What that means, I'm going to write m over n multiplied by itself 7 times. M over n multiplied by m over n multiplied by m over n. And of course, I'm going to do this 7 times. So that's the 4th, the 5th, the 6th, and the 7th. And because of how multiplication works, you multiply the numerators together. So we have 7 m's multiplied, 1, 2, 3, 4, 5, 6, 7. So we have m to the power 7. And we have 7 n's multiplied, n to the power 7. And so the exponent got distributed to the numerator and the denominator. And there we have the rules, basic rules of exponents. A couple more rules we want to know. What if the exponent is 0? What does that mean? And what if we have a negative exponent? So let's take a look at this first one here. If we have a raised to the power 0, then as long as the base is not 0, the answer is going to be 1. Any number raised to the power 0 is going to be 1. And if you raise a number to a negative exponent, it's the same as flipping that expression and changing the exponent to a positive. And I'm going to show you how that works right now. So let's talk about the 0 exponent. Now, let's talk about the reason for that. And it's kind of a it's kind of a proof. Let's say I raise a number to its a power a to some power n, and we're assuming that a is not 0. And I'm dividing it by itself. Well, I could write that as 2 different ways. I could write it as a divided by a to the n divided by a to the n. And of course, any number divided by itself is 1. And that's the same thing that as saying a to the power n. I'm going to rewrite that as a to the n divided by a to the n. Can be written as a to the n over a to the n. It's the same thing to its own exponent. So let me just rewrite that here. And a to the n divided by a to the n is the same as a to the n over a to the n. Now, as you can see, that means we can subtract the exponents, and that gives you a to the 0. So now there's a property of real numbers called the transitive property, which basically says that if a to the n divided by a to the n equals to 1, and that same expression gives you something else that looks different, those two things are actually the same thing. So a to the 0 and 1 are the same thing, provided that the base is not 0. And therefore, generally speaking, we can then say any non-zero number raised to the power 0 is going to be 1. Whether that number is a fraction, or a decimal, or a negative, as long as that number is raised to the power 0, your result is going to be 1. The only time that doesn't work quite like that is when the base is 0, and in that case, that's a different condition that involves some calculus for us to analyze that situation. Now, let's see what's going on with negative exponents. If we bear in mind that rule that we just did, that if you raise something to the power 0, then you get 1, then we can always say, oh, well, what if I have a to the negative n? Well, let's see what a to the negative n really means. A to the negative n is really a to the 0 minus n. Negative n is just 0 minus n. But as we saw before, when we subtract exponents, that's because we were dividing the two terms with the same base. I'm working kind of backwards. That's the symmetric property of equals. So a to the negative n is really a to the 0 minus n, which is really a to the 0 divided by a to the n. If you think of it that way, that makes sense. So it should make sense the other way as well, because equals works that way. And we just saw that a to the 0 really is 1 as long as the base is not 1, which in this case it's not. And then a to the n is just a to the n. So we just see that, so if a to the negative n is just the same as 1 over a to the n. A way of thinking of it is we move it to the denominator. So I'm going to give you an example here. Let's say I have 5 to the power negative 3. I can think of that as 5 to the negative 3 over 1. And then I consider it as if I moved this 5 to the 3, negative 3 to the denominator, and that causes me to change the sign of the exponent to a positive 3. Nothing else changes, and 1 is multiplied on top. So we'll leave it up there. By the way, if the exponent was a positive to begin with, and I do that same process, the same thing happens. I will rewrite the thing as the expression as a fraction with a denominator of 1. I would move the term to the denominator, and that will give me 1 on top and change the sign of the exponent. And in fact, if I can go the other way around as well. So let's say I have something like 1 over p to the negative 3. Well, I could then move that p to the negative 3 to the numerator, just like I did with the denominator, for the same reason. But this time, the exponent now is going to change p to the 3, and they were just going to leave a 1 at the bottom, which we can just write as p to the 3. And again, same thing would work if it's a positive exponent, that would change as well. Now, there are a few things that we want to bear in mind. So I left the rules here as a summary with a few examples to illustrate. This is taken from one of the textbooks. Product property, multiplying with the same base, division property, dividing with the same base, power rule, raising a power to an exponent, product of a power, multiplying two things and then raising it to an exponent, product of a power of a quotient, dividing two things and raising that to an exponent. And that's what we just went through. So we have that. Now, special situations. What if you raise 0 to an exponent? Well, if you raise 0 to a positive exponent, you're going to get 0. 0 to the power 0 is undefined. It's actually a calculus question. But if you raise 0 to a positive exponent, you get 0. If you raise 0 to a negative exponent, that's undefined because effectively you will be dividing by 0. If you raise 1 to any exponent, it's 1. Whether it's a positive exponent, negative exponent, or 0, 1 raised to any exponent is 1. Also, please bear in mind that if you have a product and something is raised to an exponent, the exponent only applies to what is directly above, not to both things unless they're in parentheses. So if I have a times b to the n, that's the same thing as saying a times b to the n. The n is only for the b, not for the a. So we're multiplying a times n factors of b. Here's an example. If I have negative 5 squared, that square is only for the 5, not for the negative. So really it's negative of 5 times 5, which is negative 25. If I wanted to apply to the negative as well, I put the negative 5 in parentheses, and then I have negative 5 squared is equal to negative 5 times negative 5, which is 25. And here's another example. 7x to the negative 2. That negative exponent is only for the x, not for the 7. So it's really 7 times x to the negative 2, which I can then write as 7 times 1 over x squared, which is 7 times 1 over the x squared at the bottom. Before we go on to some examples here, I want to point out one more thing, which is, and we won't go into detail with this situation, we are there's another thing to consider, which is rational exponents, and that's for another lesson. But I want to have us make sure we're clear about the definition of rational exponent. When you have a rational exponent, the numerator of the exponent is the power, and the denominator is the root that you're taking. So b to the m over n means you're taking the nth root of some number b, and then you're raising that to the power m, or you're raising b to the power m and then taking the nth root of that. Either one of them is the same. So the nth root of b to the m, or the b to the nth root of b and that number raised to the power m, means the m is the numerator of the rational exponent and n is the denominator. N is the root that we take. Here's an example. B to the 2/5 means you're raising b to the power 2 and then you're taking the fifth root of that. And so we should make sure we understand those rules. Also, please be careful. Exponents distribute over multiplication and division, but it doesn't do so over addition and subtraction. So if you have x plus y to the n, that does not mean you get x to the n plus y to the n. That is a false concept. It doesn't work that way with real numbers. It's likewise with subtraction. Exponents do not distribute over addition and they do not distribute over subtraction. They only distribute over multiplication and division. So let me explain to you why that is with an example, or you can call a counterexample. If you have 2 plus 3 to the power 4, and we use PEMDAS, we will do what's in the parentheses first. 2 plus 3 is 5, and 5 to the power 4 is 625. However, if I did 2 to the 4, 3 to the 4, which would be the case if you had this, if you could have distributed the 4. 2 to the 4 is 16, and 3 to the 4 is 81. When you add those, you get 97. It does not give you the same result. That means that 2 plus 3 to the 4 does not give you the same answer as 2 to the 4 plus 3 to the 4. So we cannot draw that conclusion about addition. Likewise with subtraction, if I said 7 minus 3 squared, if I did 7 minus 3, that would be 4, and 4 squared is 16. However, if I did 7 squared minus 3 squared, that would be 49 minus 9, which is 40. Clearly different numbers here. So 7 minus 3 squared is not the same as 7 squared minus 3 squared. So be careful that you do not distribute over addition or a subtraction. Now, let's talk a little bit about, let's do some examples here with exponent rules. All right, so firstly, let's start off with this quick example here. This says simplify this expression, 2 over 3 raised to the power negative 2. Now, we have two ways we can do this. We have a rule that says if you have something raised to a negative exponent, you can distribute the negative exponent to each term, if it's a product or if it's a quotient. This is a quotient. So that means I could say this is the same as 2 to the power negative to the negative 2 exponent over 3 to the negative 2 exponent. Now, since the exponent is negative, I can actually then move this guy, the denominator, to the numerator. And I can move the numerator to the denominator. I just have to make sure that I change the signs of the exponent. So now this 3 to the negative 2 in the denominator becomes a 3 to the positive 2 in the numerator. And a 2 to the negative 2 in the numerator becomes a 2 to the positive 2 in the denominator. And then we can work it out. 3 squared is 9, 2 squared is 4. The answer is 9 over 4. So that's one method. Another method is to actually do the flipping first. I can actually flip the fraction. When I flip the fraction, 3 over 2, it becomes a positive 2. So what I did was I flipped the fraction and then changed the sign of the exponent. Flip fraction and change the sign of the exponent. And then after that, I'll just distribute and simplify. So now I'm going to distribute the 2 to the 3 and the 2 to the 2. And now we have 3 squared over 2 squared, and that equals to 9 over 4. We get the same answer in either case. I'd like you to try this one on your own. You can pause the video and then attempt it. So now let's go on and do this one. What I'm going to do is do the second method. I'm going to flip the fraction and change the sign of the exponent to a positive. Then I'm going to distribute this. Well, this is just the same as 3 squared. 3 over 1 is just 3 squared. 3 squared is 9. Now, I'd like you to try these on your own and then check the video to see if you got those answers correct. Let's take a look at this one. Since that's a negative exponent, then we can rewrite it as 1 over 5 squared. And 5 squared is 25. Make sure you write your exponent small enough so it's clear as that it's an exponent. Likewise, 8 to the negative 1 over 8 to the negative 2 is 1 over 8 to the positive 2. And that's 1 over 64. If you have a negative in front of the expression, only the exponent only applies to what it is directly over. So that negative is practically a negative 1. It's actually a negative 1 times 5 to the negative 2. So we can write the negative 1 on top and the 5 to the positive 2 at the bottom. And that gives us negative 1 over 25. Let me illustrate that here again. This is the same as negative 1 times 8 to the negative 2. That's negative 1 over 8 squared. And that is equal to negative 1 over 64. But if we have the negative inside the parentheses, as I did in the example, then the exponent is for both, and then I just have negative 5 squared in the denominator, the whole thing, keep my parentheses. When I square negative 5, I got a positive 25. And as you can see, it would be the same for negative 8 raised to the power 2. We get 1 over 64. And so we're going to keep going here. I'm going to flip this negative to a positive. So I flip the fraction. I get 4 over 1 cubed. 4 over 1 is just 4. So that's just 4 cubed. And 4 cubed is just 64. For this one, it's just 8 over 3 to the power 1. And anything raised to the power 1 is just itself. In this case, we have a negative 3/2. So what we will do is we're going to decide which one of these will be the negative. I can put the negative in the numerator and the denominator. And I'm going to also flip the fraction because of the negative. So really, I'm going to say, let's say we choose the top to be negative. So I have 2 over negative 3, because when I flip that now, the negative's at the bottom. And then I can distribute the exponent to each part. I get 2 to the 4 over negative 3 to the 4. I would have got the same result as if I did the negative on the numerator. So I end up with 16 on top and negative 81 at the bottom. Positive 81 at the bottom, sorry. Because when you raise a number to a positive, an even exponent, the result is positive. When you raise a real number to an even exponent. Likewise, if we do this, we get negative 9 over 1 squared, which is just negative 9 squared, which is just 81. And then for this one, there's a negative outside. So we keep that negative outside, and we flip the fraction because it's a negative exponent. Flipping the fraction doesn't change the sign in front of it. It only changes the sign of the exponent. And then, so the negative is still going to remain in front while I distribute that exponent. Because again, that exponent is only for the inside the parentheses, not for the negative. So I'm kind of tight with space here. but 5 cubed is 125 and 2 cubed is 8. So the answer for that one is 125 over 8. Likewise, if I flip this fraction, I get negative quantity 2 over 1 to the 5. And that is simply going to be the negative of 2 to the 5, which is negative 32. Now, let's take a look at this one. We could always distribute the 0 to each term, but the parentheses means we're raising the whole thing to the power 0, and anything raised to the power 0 is 1. So for number 32, the answer is 1. Now for this one, number 33, we have to be careful because 0 is only over the b, not over the other terms. So that 0 only applies to the b, not to the 10 or the a. So this expression is really 10 times a times 1, because b to the 0 is 1. And so the answer is 10a. Likewise, the 0 is only for the 0 exponent is only for the x, not for the 13 in this number 34. So the answer then is 13 times 1, which is 13. Let us continue with some more examples here. And as I said before, I strongly recommend that you try these examples on your own first, and then check back to see if your answers match with my answers. Okay? Now, since we're multiplying two numbers with the same base, we simply add the exponents. X to the 4 plus 8, and after a while you don't need to show this step, but it's just to illustrate it for the sake of the notes. So that we get x to the 12. And if we're dividing, then with the two numbers with the same base, you simply subtract the exponents. Numerator exponent minus denominator exponent. So we end up with 13 squared, which, since that's a small enough number, we can just work it out as 169. And then we have z to the 3 raised to the power 4. So, and I write my z's with a slash through them so that they don't get confused with a 2. But really what we're doing here, we're multiplying the exponent. That's the rule there that we went through earlier in the lesson. And so the result is z raised to the power 12. Likewise, we can distribute an exponent to each term. So with this situation, I'm going to show all the steps that are going on, but sometimes you can just combine two steps. This is 3 to the power 4, and then we're raising x squared to the power 4. And then 3 to the power 4 is 81, because it's multiplying 3 by itself 4 times. And then x squared to the power 4 means you're raising x to the 2 times 4, and 2 times 4 is 8. So it's 81x to the 8. When you have a negative exponent, you just think of it as q to the negative 5 over 1, and you move it to the denominator. Once again, you don't need to show this intermediate step, but I just want to use it for the sake of the notes. So we end up with 1 over q to the positive 5. Once again, since we are multiplying two numbers with the same base, I simply add the exponent. 7 to the 10 plus negative 13. Well, 10 plus negative 13 is negative 3. So that means I can then flip this and have 7 to the 1 over 7 cubed. I'm going to put a slash through my 7. And so 7 times itself 3 times is 343. So we have 1 over 343, and we're done here. Now for this one, number 48, you can actually think of it two ways. You can think of it as, wait, we have 4 fours up here, 4 t's up here, and 8 of them down here. These 4 up top can cancel with 4 of these at the bottom, leaving 4 of them behind. Let me write that down this way. T to the 4, and then I have t to the 4 times another t to the 4. And then that would mean that these 4 cancel with those 4, leaving the 4 below and just a 1 on top. Or we can say that's equal to t to the 4 minus 8, which is t to the negative 4. And then we just flip that and get 1 over t to the 4. Either way, you get the same answer. There's more than one way to look at these. Number 49, and again, I remind you, you can do these on your own and just, check the answers. So a to the negative 2 times a to the negative 5 is a to the negative 2 plus negative 5. And that gives us negative 7. A to the negative 7. And a to the negative 7 is the same as 1 over a to the positive 7. Do not rush these types of questions. Take them step at a time. Now again, there are 2 ways to do this one. Method 1 is to just apply the rule. And method 2 is to say, hey, we have a negative 1, s to the 1 up top. You just move the negative down to the bottom. And then now we have 1 over s times s, because that's s to the 1, times another s to the 1. And that gives you 1 over s squared. Or you could say this is the same thing as s to the negative 1 minus 1, which is s to the negative 2. And that's the same as 1 over s squared. Either way gives you the same answer. So if you take a look at these here, I can do it either way. I'm going to just choose a method here. I'm going to move the negative 6 to the denominator. And again, there's multiple ways of doing this one. I get 1 over z to the positive 6 times z to the negative 2. When I add positive 6 plus negative 2, I get positive 4. So I got z to the positive 4. And I move the negative 6 to the bottom here only because they have the same base, and I know that this will give me a bigger result but positive, and that will swallow up the negative. In this case, we have 2 different bases, so we cannot combine them. But that d to the negative 1 has a negative exponent, so I'm going to switch it to the top, and that gives me c to the 4 times d to the 1, which I'll leave as that. That's right, that's d to the 1, so it's c to the 4d. And then with this one here, since this has, the whole thing is raised to the power of 0, the result is 1. And again, we're assuming that our numbers are positive numbers here. Now, let's do a little more work with PEMDAS here. 2 to the 4 plus 2 to the negative 2. Well, 2 to the 4 is 16. 2 times itself 4 times. And 2 to the negative 2 is 1 over 2 squared. So basically, this is 16 plus 1/4, which is 16 and 1/4, which I can then multiply, write as an improper fraction. 4 times 16 is 64 plus 1 is 65. 65 over 4. Let's move on. We have 4 to the negative 2 plus 2 to the negative 2. We can rewrite those as 4 to the negative 4, 1 over 4 squared plus 1 over 2 squared. Again, remember, you cannot distribute an exponent over a negative, so you cannot combine 2 things with the same exponent if they're added together. You could do that if they were multiplied, but not if they were added. So this becomes 1 over 16 plus 1 over 4. And of course, you can add the fractions together. That is 1 over 16 plus 4 over 16. That's 5 over 16. There we have that. Let's go with this one. 4/5 to the negative 1 is the same as 5 over 4 to the positive 1. And I'll leave that for now. And then 3 over 2 is the squared is 3 squared over 2 squared. And then minus 2 over 7 to the 0 is just minus 1. So we have 5 over 4 plus 9 over 4 minus 4 over 4. So 5 plus 9 is 14, minus 4 is 10. So we have 10 over 4. 10 over 4 is the same as 5 over 2. Once again, there are more than one ways to do this. We could have simplified each fraction first and then combine them, or I could have just put these two together and then subtracted 1 from the result, but we would have gotten the same answer. All right, let's try a few more examples here. These look a little bit more complicated. So let's see how we do them. Now, in this case, what I'm going to do is I'm going to put the m's together and the n's together. And the negative exponents, I move them so that they become positive exponents. So the n to the negative 1, I'm going to move to the denominator. And the n to the negative 2, I'm going to move to the numerator. And that will now give me n cubed times n squared over m to the 1 times m to the 4. Then it becomes a simple process. N to the 5 divided by m to the 5, which we'll leave as that. Now for number 67, we want to do a little extra thinking here. I'm going to do it in this format. I'm going to divide the numbers together, and I'm going to divide the matching variables together. And I'm going to leave out a bit of a step here, partially because of space, but partially because it's a concept. Negative 48 divided by 32, the common factor is 16, so I can write this as negative 3 over 2. I'm going to extend that a bit. We have 1a in the numerator, and we have 4 a's in the denominator. So in a sense, I can take off one of these a's and one of these a's and leave only 3 behind. Likewise, I have 3 b's in the denominator and 10 in the numerator. I can take off 3 of those b's and leave 7 of them behind. So what will be left over is 7 b's in the numerator, which is b to the positive 7, and 3 a's in the denominator, which is a cubed, which I will then multiply by the fraction negative 3 over 2. So my answer becomes negative 3b to the 7 over 2a to the cubed, 2a cubed, 2a to the power 3. Now, once again, a question like number 70 could be done multiple ways. The method I'm going to choose to use here is to distribute the exponent first. And I'm not saying my way is the best way, but this is one of the ways it could be done. So when I do that now, I have negative 6 to the power negative 2, a to the negative 2 to the power negative 2, and then b cubed to the power negative 2, and then c to the negative 2. And negative 6 to the power negative 2 is 1 over negative 6 squared. And if I multiply the exponents for a to the negative 2, a to the negative 2, that gives me a to the positive 4, which I'll write over 1 because it's in the numerator, and then times b to the negative 6, which I'll write over 1, times c to the negative 2, still over 1. So what I will now do, for the sake of space, create a little extra space here. Hopefully that will be sufficient for what I'm doing here. That gives me a to the positive 4 in the numerator, and then in the denominator I'll have a 36 because negative 6 squared, and then the b to the negative 6 will be moved to the denominator. So will the c to the negative 2, and that will give us b to the 6 c squared. Okay, and that is our answer. A to the 4 over quantity 36 b to the 6 c squared. And I'm a little tight here in my process, but hopefully again I'll have enough space to complete these. If not, I'll just leave them for the viewer to complete. Now, there's no exponents outside, so I can just do a quick little multiplication. I'll multiply the 4 by the -1, which is from this here, the m to the -2 times the n to the m to the +6, and the n times n to the -3. And I'm going to write that n as n to the 1. So 4 times -1 is -4. And then m to the -2 times m to the 6. We're adding those exponents, so we get m to the +4. And n to the -1 times n to the -3. That is going to give us n to the -2. Which I can then move to the denominator, and my answer becomes -4m to the 4 over n squared. And again, the best way to get good at these is by lots and lots of practice. Now let's go on to this one here. P to the -2 q to the 3 times 2p to the q to the 4 squared. Because of space, I'm going to just distribute and operate at the same time. So this gives me p to the -6, because I multiply those exponents, times q cubed times 2 squared is 4, p squared, q to the 4 times 2 is 8. Then 4 will be the leading term, coefficient here. P to the -6 times p squared is p to the -4, and q cubed times q8 is q to the 11. So that will give me 4q to the 11 over p to the 4, because the negative exponents puts the p in the denominator, and they do not want negative exponents in the answers. Let's move that down slightly. Let's move on. Then we have this example here. We distribute the exponents again. So we get x to the 6, 2 times 3 is 6, over y cubed, then times 5x squared y. And what I'm going to do is say, well, I'm going to do a little thinking here. The 5 is in the numerator. X to the 6 times x to the 2 is x to the 8. And then this y on top will cancel with one of the y's at the bottom, leaving just y squared. And I can show that by saying that cancels with one of these, leaving 2 of them behind. And there we have it. 5x to the 8 over y squared. Let me just put that into a little box here. Now let's do number 78. For number 78, we're going to distribute the exponent and simplify. So we have -3 squared is +9. X squared is x to the 4. Y cubed squared is y to the 6. Over -2 cubed is -8. X to the 3 is x cubed. And y to the 4 cubed is y to the 12, because we multiply the exponents. And then there you can start seeing something interesting. We have the 9 on top because it doesn't simplify with the 8. We have 4x's in the numerator and 3 in the denominator. So if you see the cancellation there, there's only 1x left on top. There's 6y's on top, but it's 12 at the bottom. If you do the cancellation there, there's only there's 6y's left at the bottom. So you can start doing a little cancellation. That cancels, leaving, and 4 of these cancels, leaving just the 1x. This cancels, and those cancel, leaving just the 6y's. And that's our answer. Now let's take a look at number 79. With this one, we have a negative exponent and we have terms in the parentheses. So let's do this. Let's simplify what's in the parentheses first. Then this should be the exponent. And let's see, that's one way to do it, but it's not the only way. So we know that negative 2 and 3 have nothing in common. But I can move that x to the numerator because it's a negative exponent. So I have x to the 6 on top. And then I'm going to put the x squared on top as well. And then for the bottom, I have y to the 4 at the bottom. And then I'm moving this negative exponent to the bottom. So it's y to the 5. And then I have that to the negative 3. When I simplify that, I get negative 2x to the 8 over 3y to the 9. And then here's the thing. This is raised to the power negative 3. So I'll flip the whole thing and I have 3y to the 9 over negative 2x to the 8. All of that now is raised to the positive 3 because I changed the sign of the exponent. When I distribute the exponent, and I'm going to kind of squeeze it in here, change the sign of the exponent. 3 to the 3 is 27. Y to the 9 cubed is y to the 27. Multiply the exponents. Negative 2 cubed is negative 8. And x to the 8 cubed is x to the 24. Again, multiply the exponents. And that's our answer. That's one method of doing it. It is not the only method, but that's the one I chose to use to do this question. All right, let's do a few more of these and then move on. For number 82, I'm going to do it the other way. First, I'm going to flip it, then I'm going to simplify. Now, I know that c to the 0 is already 1. So I have a to the negative 1. Well, let's do it this way. Distribute the exponents first. So I have a to the negative 2. A cubed to the negative 2 is a to the negative 6. B squared to the negative 2 is b to the negative 4. C to the 0 was 1, so that's just raised to the power negative 2, which is just 1. A to the negative 1 raised to the power negative 2 is a squared. B to the negative 2 raised to the power negative is b to the 4. And c to the negative 3 raised to the power negative 2 is c to the 6. Then I will move my negative exponents to the denominator, and my positive exponents will stay. So what will end up happening is I have only 1 on top, and then a squared times a to the 6, b to the 4 times b to the 4, and then c to the 6. That will give us 1 over a to the 8, b to the 8, c to the 6. And that's our answer for that one. That one is a little bit tedious, but that's the way you do that. All right, just because of time and space, I'm going to leave you to do number 84. Now let's go on down to number 108. Please note here they say simplify the expression A and B represents positive integers. So we add, well, since we're multiplying two numbers with the same base, we simply add the exponents. So we have A minus 5 plus A plus 7 are the exponents of y. A plus A is 2A. And negative 5 plus 7 is positive 2. And that's that. It's pretty easy. Now try number 111 on your own. And then you can check the video afterwards. So for this one, what I would recommend is that we split this up to be x to the 3b minus 2 minus quantity 2b plus 1, and then times y to the b plus 1 minus quantity 2b plus 2. Let's simplify that. So we get x to the 3b minus 2 minus 2b minus 1, and then y to the b plus 1 minus 2b minus 2. Continuing with that, 3b minus 2b is b, so we get x to the b, and negative 2 minus 1 is minus 3. Then, and then b minus 2b is negative b, and 1 minus 2 is negative 1. So that's as a negative exponent. So I can then rewrite that as x to the b minus 3 over y to the b plus 1. Change both signs because you're making the whole expression negative, the whole expression of the numerator negative, of the exponent negative, and so that is our result. There we go. Now let's finish up here and go into solving the scientific notation. Scientific notation is very useful in science and typically goes well together with significant figures, which I won't talk about in this video. Basically, what a scientific notation does is takes a number and writes it as a non-zero number, as a whole number, a number between 1 and 9 inclusive as a whole number part, and the rest as a decimal. And then we compensate by multiplying by a power of 10. So it takes a very large number and makes it into a small number, or a very small number and makes it into a large number, so you can read it. It's a standard notation. So let's take a look at this number here. It's 240 trillion. So when there's no decimal indicated, the decimal is at the end. What we want to do is move the decimal to the first non-zero digit on the left. So we're going to move the decimal to right here, between the 2 and the 4, so because it's coming right after the first non-zero digit, right after the first non-zero digit. So we move it. Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So that means we have moved the decimal point 14 places to the left. It was at the end on the right side, so I moved it 14 places to the left to get it between the 2 and the 4. That means I have to compensate by multiplying by a power of 10 to the positive 14, like moving the power to the right 14 places. If I move the decimal point to the left, I move the power of 10 to the right by the same amount. So this now can be written as 2.4 times 10 to the 14, and then we can make necessary adjustments based on significant digits and so on. Here's another example with a small. Now in this case, we're trying to move the decimal to the right, so it comes after the 3. It's indicated here. How many places do we move it? We're going to move it 1, 2, 3, 4, 5, 6, 7. But we're moving it from this position to the right 7 units. So I compensate by multiplying by 10 to the negative 7. That's like moving the to the left on the number line for the exponent of 10. So this number becomes 3.6 times 10 to the negative 7. Let's do an example. Well, a few examples. So write this number in scientific notation. So we're going to move this number, and this is basic stuff. So, many people already learned this in elementary school. You move this 1, 2, 3 places to the right, and that becomes 4.2. And I compensate by moving the exponent of 10 to the left 3 places, so it's 10 to the negative 3. In this case, I'm moving this number to the left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So the answer for this one becomes 6.02. 3 significant figures here times 10 to the power. Since I moved 23 power units to the left, the exponent moves 23 units to the right. And then this last one here, very simple, 4.6 times 10 to the 1, 2, 3, 4 units. Negative 4. Since we move the decimal to the right, then we move the exponent of 10 to the left. Write the numbers in standard notation. So the number of $20 bills in circulation was this. Since we're talking about 10 to the 9, this now we're unraveling the scientific notation. So the 10 to the 9 says move to the right 9 places. So we have 5.1, 2, 3, 4 places, but we still have 9 spots. So we have 5 more to go. So I fill the spaces with zeros. And that's my answer, and I can put my commas after each block of 3 numbers. So there we have it, 5,282,200,000. In this case, we're moving 5 units to the left. So if I think about that, then I'm going to be starting where this number is and going 1, 2, 3, 4, 5. And I'm filling in the spaces. So I have 1, 2, 3, 4 spaces to fill in with zeros. 1, 2, 3, 4 spaces, and then I have my 1 and my 8. But I put my decimal here, but because I don't want this to be overlooked, the decimal to be overlooked, I put an additional 0 saying that's no whole numbers there. Finally, with this one, again, as before, we're moving this number to the right 9 units, but we have 3 decimal places here, so we need 6 additional zeros. So we have 6, 3, 7, 8, and then 6 additional zeros. And there we have it. Lastly, when you're multiplying using scientific notation, you simply multiply the corresponding numbers together and then adjust with the exponents. So we have 3.26 times 8.2. 3.26 multiplied by 8.2. And what I would do is multiply the whole numbers. So we have 3.26 times 10 to the negative 6 multiplied by 8.2 times 10 to the 9. I multiply 3.26 times 8.2, and then I multiply the powers of 10 together using integer rules, exponent rules, sorry. So let's see how that works out. 3.26 times 8.2 is 26.732. So we end up with 26.732. And then when I multiply the exponents, I'm multiplying 10 to the negative 7 by 10 to the negative 6 by 10 to the 9. I add the exponents, I get 10 to the 3. This is still not in scientific notation because I have to move the decimal point one place to the left. When I move it to the one place to the left, I now get 2.6732, making the number appear smaller. And to adjust for that, I have to move the decimal point, the exponent of 10 to the right to make that bigger. And there we have it. Let's try number 97. I'm going to rewrite this as 2.4 times 10 to the 1, 2, 3, 4, 5, 6, negative 6. And I'm multiplying by 6.7 times 10 to the 3, 6, 9. So now I multiply 2.4 by 3.7. Not 3.7, by 6.7, sorry. 2.4 times 6.7, that gives me 16.08. And then I add I multiply the powers of 10. 10 times 10 to the 10 to the power negative 6 times 10 to the power 9, 10 to the 9. And I add the exponents. Negative 6 plus 9, as we just saw, is 3. So we get times 10 to the 3. I move the decimal point one place back. So I move the exponent of 10 one place forward. To compensate, I get 1.608 times 10 to the 4. Now for this one, I'm going to write this as a fraction. So I have 8.5 times 10 to the negative 2 over 2.5 times 10 to the negative 15. And then I see that this is the same as 8.5 divided by 2.5 and then times 10 to the negative 2 divided by 10 to the negative 15. 8.5 divided by 2.5 is 3.4. So I end up with 3.4 here. And then times 10 to the negative 2 divided by 10 to the negative 15 is, if you move the 10 to the negative 15 to the top, you get 10 to the positive 15, which is added to the negative 2, you get 10 to the 13. And there you have your answer. I won't show all of that work, but you can do that on your own. In this last example here, I'm going to rewrite that as a scientific notation. I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's 10 to the negative 10 divided by 8.0 times 10 to the 3, 6, positive 6. So I have 2 over 8, 2.0 over 8.0 times 10 to the negative 6 over 10 to the negative 10 over 10 to the negative 6. Since I want to make this into scientific notation, I'm going to have this as 2 divided by 8 is 0.25. And then this is times 10 to the negative 16. I'll leave you to see how I got that. And then, it's a positive 6, sorry. So then I move the decimal point one place to the right, and that leaves me with 2.5. If I move the decimal place one place to the right, then the exponent gets moved one place to the left. So I get negative 17. Remember, we're moving to the left on the number line. And there we have our results. And that takes us to the end of this lesson. So scientific notation is just an application, really, not just, but it's, among other things, an application of exponent rules. And so I strongly recommend that you go on and practice some of these on places like Khan Academy, OpenStax, and in your textbook, depending on what the textbook is. And as usual, as I say, you only get good at math by practice, lots and lots of practice. And you should try the word problems related to this topic or any topic that you do. OpenStax.org has an app, OpenStax, OPENSTAX. Khan Academy also has an app that you can use for videos and practice that also covers similar concepts as these. All the best and continue learning.